premise of our session is that the more we know about the mind's design, the more we can improve thinking and learning, the purpose of education. We begin from a foundation that by understanding the mind, we can more effectively guide its development. Development that includes acquiring knowledge and the ability to think well. If this holds true, we have a promising basis for improving education. Let's start by defining a few terms to be on the same page. Throughout the presentation, I'll use the terms brain and mind. It's important to note that these aren't the same. And though I'm oversimplifying it, we'll consider the brain as the physical organ in the body, and the mind as the mental processes, thought, and consciousness, or the activity of the brain. Let's also define brain-based learning. For our purpose, I'm categorizing it as strategies that use as at their foundation the science of how the brain operates. Brain-based learning rests on the principles of cognitive neuroscience and cognitive science. Cognitive neuroscience is the study of biological processes occurring in the brain that support cognition. It's a discipline that includes the study of the brain along with psychology and education. It's a branch of neuroscience. Cognitive science, on the other hand, is the specific study of the mind and its processes. Cognitive science is also an interdisciplinary study of how information is represented and transformed in the human brain. It's also interdisciplinary in nature, including psychology, neuroscience, learning sciences, linguistics, sociology, and education. There have been tremendous advances in neuroscience in the past 2 decades. In 1990, President George W. Bush declared the decade of the brain. Since that time, scientists have greatly advanced our understanding of the brain. Neuroscience is at a historic turning point. In the decades after Decade of the Brain, a continuous stream of advances has shattered long-held notions of how the human brain works. These advances have also reshaped other fields: psychology, economics, education, and law. Until the Decade of the Brain, scientists believed that once childhood development was over, the adult brain underwent very few changes. Since then, neuroscience has steadily built the case that the human brain, even when fully mature, is much more plastic, or changing, malleable, than we originally thought. It turns out the brain at all ages is highly responsive to environmental stimuli, and the connections between neurons are dynamic and can rapidly change within minutes of stimulation. In reality, our brains are much more capable of recovery and rewiring than we ever knew. Neurogenesis is the ability for new neurons to be created. It is the process by which the brain is able to respond to its environment. Neuroplasticity is the brain's ability to be fashioned by its own processes. It's able to be changed, and it's malleable. You can think of neuroplasticity as the experiences that we have leave imprints on our neural pathways. You've probably heard the expression, neurons that fire together, wire together. This is a way of saying that what we choose to concentrate on grows and expands. In this session, we'll explore principles of how the brain works and the role of brain-based learning in developing cognitive skills and the exciting developments in brain research. The more we understand the brain and the thinking processes, the better equipped we are to structure our curriculum, our instruction, our assessments, and all of our educational initiatives. So let's look at the adult brain. Much of the research dollars that have been spent on learning and cognition have been focused on childhood. It's a great foundation of knowledge, but it doesn't exactly fit what we're doing on a daily basis. So let's explore the brain-based learning and the adult learner. We're going to look at 3 areas. First, brain plasticity, or the neuroplasticity that we were just talking about. The human brain has an amazing ability to reorganize itself by forming new connections between neurons. Now, conventional wisdom has told us that the brain is only able to be changed during childhood. We're also going to look at sensitive periods, or periods during which the brain is more responsive to input from the environment. Conventional wisdom told us that these only occur in childhood. We'll also take a minute to look at attention, or the ability to control distracting stimuli. It allows us to focus. Let's look at each. Brain plasticity. Science tells us that there's a gradual reduction in brain plasticity. One theory is that early learning stabilizes neural pathways. Later in life, it is more difficult to overcome those pathways when new information is presented. Think about the challenge of learning a new language in adulthood. Achievable, but certainly more difficult than in childhood. Let's look at sensitive periods. Science tells us that the greatest number of sensitive periods does occur in early to mid-childhood. The number of synapses, or connections between neurons, is baseline established then. However, we know that new neurons are formed throughout life. Based on the current research, sensitive periods are not a serious limiting factor, but they do establish changes in the expected rate of learning. In adulthood, it may take longer to learn the same content. And lastly, attention. Attention is the ability to control distracting stimuli, and it occurs in childhood. Adults are selective, while the child is immersive. Adults need to respond to stimuli in order to learn from it, while a child can be passively perceiving the same stimuli and still learn. The reality of this research indicates that there are challenges to the adult brain and learning. However, learning is achievable across the lifespan. As learners, educators, administrators, and policymakers, we need to understand both the strengths and the limitations of the adult brain when designing educational programs. Cognitive architecture was an early view of how the brain operated before the decade of the brain. The information processing perspective of the brain in the 1950s and 1960s created many comparisons between the human mind and, at the time, emerging computer technology. In thinking about the brain as a computer, it has helped us to understand memory and how we transform information. For example, this metaphor helps us to understand how information moves through the brain, from the sensory register, or the first stop in the mind after information comes in from our senses, how it moves to the short-term memory, and eventually to the long-term memory, or the warehouse of the mind, where we store everything we know, and we're able to cross-reference that information. But this metaphor has its limits. The brain is not like a computer. We have purpose, we have values, emotions, and personality, consciousness, things that make us distinctly human. Though imperfect, the computer metaphor helps us to understand the memory structures of the human cognition. These research realities have produced some laws of learning. Let's explore 3. First, we're going to look at the serial position curve. Learning is complex. We learn at different rates of speed. We may pick up some things quickly, while others take time. In this sense, learning is not linear. However, there is one sense where learning is linear, and that's when we're learning across the linear dynamic of time. When students read our guidance or watch a video, those ideas follow in a sequential order. It raises the question, how does learning relate to the presentation of ideas in a time sequence? As you can see from the graphic, the serial position curve is U-shaped, and it suggests that we remember more at the beginning and at the end of an experience. So what's the practical application of this? Well, we know that the beginning and the end are the most important. Consider your online classroom, the first couple of minutes, or the week, the introductions. Carefully craft your initial messages, your guidance, and also think about how you finish. Key weekly summaries. This may also help you provide strategies for studying for your learners, perhaps starting with outlines or finishing with key takeaways. Encoded specificity principle is basically linking the content to the context, and we see this happen both physically and emotionally. The practical implication of this is that knowledge learned in school might not easily be recalled or utilized outside the academic setting. It creates a strong justification for us to send students into the real world in their discussions. For example, if you were in the office, how would you apply this week's material? And finally, let's look at massed or distributed practice. Like the serial position curve, this explores the relationship between time and learning. It answers the question, do we learn better in a single session or over multiple sessions? Well, we know that learning is most effective when spread out over multiple sessions. But what makes this true? In relation to our brain-based strategies, each session creates its own independent memory effects. In sharing tips with your students, I'm often asked in those early Ashford classes, how can I best manage my time and schoolwork over the week? Well, now we know, if you have 6 hours to devote, they should be spread out over multiple sessions. Each of those independent sessions creates individual traces on the memory, and the more times we engage in that weekly content, multiple neural pathways are created. When recall is needed, there's a better opportunity to be successful with these multiple pathways. Promote engagement throughout the week. Now let's look at some recent brain discoveries. Researcher David Vance from the University of Alabama has been studying neurocognitive changes as they relate to aging. He researches 2 main areas that relate to learning. The first is cognitive reserve. It is really the amount and the strength of the connections between our neurons. It is from these neurological connections and the information communicated between them from which cognition is expressed. He also researches plasticity, or the ability to mold neurons, synapses, and the entire brain. We can influence the development of our brains, and we can do so both positively and negatively. Positive neuroplasticity refers to the ability of the brain to form and strengthen connections, produce positive changes, and increase cognitive reserve. Vance tells us that there are factors that promote positive neuroplasticity. These include things like physical activity, education, social interaction, intellectual pursuits, and cognitive remediation. Negative neuroplasticity is the reverse. Our daily activities can lead to the brain changing in negative ways. We can weaken those connections. We can produce detrimental changes and actually decrease our cognitive reserve. Factors that promote negative neuroplasticity include poor health, not getting adequate sleep, poor nutrition, substance abuse, depression, and anxiety. Factors that promote negative neuroplasticity can be powerful ideas that relate to the educational environment. If we have the ability to change our brain function, then we can share this knowledge to the betterment of our students. Additionally, we can use it to mold our own professional development and can offer suggestions to our students when asked. This views the ability to learn as a holistic process. So let's look at physical activity. Research on the effects of exercise in the brain are showing positive results through all stages of life. In fact, the brain responds like muscles do, growing with use, withering with inactivity. The neurons in the brain connect to each other through tree-like branches, and exercise encourages those branches to grow. It enhances brain function at a fundamental level. According to John Ratey, adding exercise sparks brain function to improve learning on 3 levels. It improves our mind's alertness, attention, mood, and motivation. It encourages nerve cells to bind to one another, and that's the cellular basis for logging new information. It also spurs the development of new nerve cells from stem cells in the hippocampus, where we create memories. Additionally, we know that toxic stress actually erodes the connection between those nerve cells. Conversely, exercise unleashes neurochemicals and growth factors that can reverse this process. Let's look at sleep. Brain functioning, and especially memory, are particularly dependent on getting adequate sleep. Much of the current research in sleep supports a 2-stage memory model. The model assumes that new memories are temporarily stored in the hippocampus. Gradually, these memories either move to the long-term storage in the neocortex, or they're forgotten. Those memories get transferred from short-term to long-term memory during sleep, especially that slow wave sleep. Sleep research has demonstrated that participants who sleep after memorizing a list of items have much greater recall and forget fewer items than participants who were tested before going to sleep. Adequate sleep is also associated with both short-term and long-term cognitive functioning. Nutrition and health. Poor health caused by disease is linked to a decline in cognitive functioning. Both the disease itself and some of the medications used to treat the disease contribute to that cognitive decline. Physical diseases with clear connections are pulmonary disease, hypertension, and diabetes. And it's not just chronic disease that affects our memory and our brain. Even when we're sick with the flu, the functioning of the hippocampus, which helps us to encode memories temporarily, is disrupted. Additionally, poor health choices like smoking or consuming excessive alcohol negatively affect cognitive performance. Finally, we'll look at stress. Sadly, we as humans are the only mammal, as far as we know, capable of self-inducing, stress-producing, fight or flight mechanism with our thoughts. In other words, we can get ourselves as worked up about a missed deadline as we can if we were being chased by an angry lion. And we can maintain that level of stress for days, weeks, months, indefinitely, even after that threat is gone. Stress is such an accepted component of our world, yet it destroys our cognitive function. It lowers our mood, increases our pessimism, increases our anxiety and irritability, and increases learned helplessness. Being in college as a professional adult brings its own inherent stress. I would encourage us to explore ways in which we could diminish our students' stress levels. I would suggest that frequent communication through email and announcements can help anticipate their questions. I hope you've enjoyed our time together. Another area of research, brain-based research of mine, is mindfulness and its impact on our learning. There are very interesting studies about how we can train our attention, and through that attention and focus, we can physically change our brain. Of course, that's another webinar for another time. But please reach out if you'd like to talk about any of these topics or about mindfulness and learning.
Thank you very much, Dr. Beattie. We do have a few minutes if anyone would like to post any questions in the chat at this time. And again, I do apologize for a little techno glitch there. I have no clue. We have no idea what happened.
Well, I think you saw most of it, so.
Yes, we did. And really, really interesting stuff. I think as time goes on, we're realizing how important a holistic view is, certainly, of education.
Sometimes we think as online instructors that we don't have the influence over our students, but often I find them asking my questions, and it's just fascinating to know that we have information that can help them in that way.
We do have a question here asking, how does cognitive architecture theory relate to personality types such as MBTI?
That would not be my area of expertise. Any follow-up questions? I mean, how does cognitive architecture, which is just the way our brain is molded, how does that relate to personality assessment?
Personality type and assessment, yeah. Interesting.
I'd have to look more into it.
PhD project. Well, I really, really want to thank you, and we're getting lots of, is it possible to get a hard copy of this terrific webinar? Is there a website to follow up on this information? There will be this particular presentation. It may be edited a little bit, but to our little technical issue there, but this presentation will be available, I think in a week or two through the CEDL. And then I didn't know, Dr. Beattie, if you had a website or a place that people could reach you if they wanted more.
Well, I'd be happy to share that information if participants want to take down my name, Ellen.Beattie@faculty.ashford.edu. I'd love to talk to you and share more information that I have.